Hi, everybody. Welcome back. So today we're going to be talking about a new type of algorithm known as amplitude amplification. And the basic idea behind amplitude amplification is it gives you a way to actually manipulate the underlying success probability of almost any algorithm that you can think of. So all of the algorithms that we've run so far, there's always been some probability of getting 0 or 1, okay? With the possible exception of Bernstein-Vazirani, which had 100% probability of giving the hidden string. Almost all other algorithms we've looked at will have some non-zero success probability. And what we'd like to be able to do is find a way of boosting that non-zero success probability all the way up to 100%. And the fundamental technique that allows us to do this is amplitude amplification. But as a particular way of motivating it, I'm going to begin by talking about a specific problem that fits really naturally inside this framework. And this problem is the problem of search. So let me just, forgot to make a bunch of blank slides. Give me a sec. Okay, that'll probably do. Wonderful. Now, let me share my screen. Excellent. So, basic idea behind the search problem is as follows. Imagine we've got a whole bunch of different boxes. Okay. And inside one of these boxes, there's cake. And what you'd like to do is you'd like to be able to figure out which box contains the cake. Okay, and the way that you are allowed to access this is through the following query model. We have a function f that will take in an argument which corresponds to one of the 2 to the n boxes. Let's call this box index x, and this function is equal to a 1 if cake is in box X and 0 otherwise. The question is, how many times do we need to be able, and let's assume that the cake without loss of generality is in box M in this case. And the question is, how many different boxes do we have to check in the worst case scenario before we find the location that the box is in? Now, you can see pretty straightforwardly that the number of boxes that you actually need to check before you know the location of it is 2 to the n minus 1. Because if we're promised that the cake's in one of the boxes, worst case scenario, it's kind of like that old saying, right? If you lose your keys, it's always in the last place that you check. So in the worst case scenario, we could envision going through the entire list, checking every single location and not finding it. If we don't find it, and we've gone all the way on to the last location, then we don't need to check the last box. We know the cake's in it. So therefore, that's 2 to the n minus 1 queries we need in the worst possible case to solve this on a classical computer. Okay. So the question is, how can we solve this on a quantum computer? Well, doing it on a quantum computer is a little bit different. So the way that a natural way of doing it would be the following. 1, create quantum superposition over all X. So the way you would do this, for example, is you could just apply Hadamard's to a bunch of zeros going in. And then we would just measure all of them. And the probability of getting the marked state in this case, well, if you got a uniform superposition, is just 1 over 2 to the n. So ideally, what we would like to be able to do is boost the success probability from 1 over 2 to the n over here to end up getting P of m approximately equal to 1. And as I said before, amplitude amplification is going to be the technique that we use in order to be able to do this. So in order for you to understand amplitude amplification, there's a couple of concepts that we need to make sure that we deal with. The first is I need to remind you of what the definition of a projector is. So a projector is a matrix that yields a component or components of a vector. So as a particular example, let's imagine we had a vector, let's call it psi uncreatively here, and we have an x component and we have a y component. And the x component I'll call psi sub x, and the y component we can call psi sub y. So if I express this in Dirac notation, then the vector, well, I'll say it's a unit vector, psi is equal to psi x plus psi y, y. Okay, but another way that we can write this is we can end up writing that psi x, as in this component down here, is then equal to the projection onto x of psi. If we go through and do this multiplication, we end up finding that this is psi x plus psi y times 0, which is just psi x. So you can see these objects in here act as projectors. But if we generalize this notion of a projector, we can actually end up saying that we require a projector to satisfy the following. A projector, P, has to satisfy P squared is equal to P. Okay, and that's more or less it. That as a consequence of this, we also have that P has to be equal to P dagger. Okay, so a way that you can end up seeing this is that if we have that P squared is equal to P, then what we have to have is that the eigenvalues of P have to be equal to 1 or 0. The reason why is that any normal matrix can always be written as P is U, D, U dagger, where these are unitary matrices, and D is a diagonal matrix. And the diagonal elements of D over there correspond to the eigenvalues of this matrix. I guess more broadly, if we don't have a normal matrix, the singular values. So P then, P squared then is just equal to U D squared U dagger, just by multiplying this through. And so P squared is equal to P implies that the diagonal matrix D, which is of the form D0, 0, D 2 to the n minus 1, 2 to the n minus 1, 0 everywhere else, this guy squared has to be equal to itself. Well, the only way that we could get this matrix squared equal to itself is if all of the matrix elements on the diagonal are 1 or 0. Because those are the only two numbers when squared equal to itself. So therefore, the eigenvalues for this are 1 and 0. A Hermitian matrix, a matrix is Hermitian if P, in this case, is equal to P dagger, or equivalently, if all eigenvalues are real. The eigenvalues are real for this, therefore it's also Hermitian. Okay, cool. And so we'll need this first part about it, to define matrices that we can use in order to just grab a single component of part of a vector. You might wonder, well, why is that? Well, if we're taking a look at this case over here where we're constructing a superposition, right? What we've got is we've got a whole, at first, a uniform probability distribution. This is P of X over X. And what we would like to do is we would like to be able to focus on the probability in box M, which is the box that contains the cake. And we would like to boost that probability up, ideally, to 1. So in order for us to really be able to discuss this, we need to be able to take the current state and pick out the component of that state that's in the direction of M. And so we're going to use this projector language in order to be able to zero in on that component of the larger vector. Okay, the second concept that's derived from a projector is a reflection operation. Okay, the idea of a reflection operation graphically is it does exactly the same thing, or it does something exactly the same as what a reflection sounds like. So, for example, let's say that what we had is I had a vector over here that has a component psi y and a component of psi x. And I wanted to reflect it about the x-axis. So if I reflected it about the x-axis, the state that I would get would be negative psi y, as in the component orthogonal to the axis that I'm reflecting about will get flipped. And of course, the x component remains exactly the same. Okay, so that is how we end up defining it. So we could define a reflection about the x-axis in the following way. So reflection about the x-axis would be equal to negative identity minus twice the projector onto the x-axis for a vector. So let's just see how that ends up working. So if we apply the reflection on our state psi, we are going to get the reflection acting on psi x, x, plus psi y, y, where x and y are again orthogonal vectors. So this will end up giving me psi x identity minus twice projection onto x, x, plus psi y identity minus twice the projection onto y, y. Oh, sorry, twice the projection onto x still. So the first off, let's take a look at the right-hand side. The projection onto x of x is 1. So therefore, just distributing, using a distributive property here of matrix multiplication, this is just psi x, x minus 2x, plus psi y, identity minus 2 times 0, because the y component is orthogonal to x. So the inner product between this and that is 0. Therefore, this is equal to negative psi x, x plus psi y, y, which is exactly the same thing that we saw graphically at the top. The y component for a reflection about the x-axis flips, and the x component ends up remaining the same. Okay, and so this operation over here, we're going to define as Rx. But we can actually think more broadly of this. What property did we end up needing in order to be able to get this to work? All that we needed to do is be able to have some projector here that specified the vectors that we wanted flipped. So this over here, if I wanted to do a y reflection, for example, I could have just changed this to y. And in this case, it would have done a reflection about y. If I had a higher dimensional space and I wanted to reflect about a bunch of different vectors, the general way of doing this would be, we would define, say, something, I'll call it R sub P, which we define to be identity minus 2 times the projector in question. Okay, so in this particular case, that would be the projector onto X. So we can end up forming a reflection from in this particular form. First thing is, well, okay, that's cool that we can talk about reflections like this, but are they unitary? Are they really things that we can build and implement on quantum computers? And the answer is totally. So let's see exactly why. So reflections are unitary. So let's work with the most broad definition of the reflection of a reflection operator that we have. We have R equals identity minus 2 times a projector. And an operation is unitary if R dagger is equal to identity. Okay, so R dagger is equal to identity, and therefore, what do we, so in order for us to evaluate this, we just need to plug this in. R dagger is equal to identity minus twice the arbitrary projector times identity minus 2 times the arbitrary projector dagger. Now, again, using the distributed property of the adjoint is in the adjoint of A plus B is equal to A adjoint plus B adjoint. We end up getting that, and the fact that P equals P dagger, we end up getting that this is identity minus twice the projector times identity minus twice the projector. Now we can multiply. Multiplying gives us the identity twice the projector times identity minus identity times the projector plus 4 times the projector squared. Now, note that the identity matrix commutes with everything. So identity times A is equal to A times the identity for all matrices A. So therefore, this is equal to identity minus 4p plus 4p squared equals identity. And this implies that it's unitary. Wonderful. So every reflection operator is by necessity then a unitary operation. And so it's something that we can build at some cost in a quantum computer. Again, you know, the way that we actually do this in practice is a little bit of an art. But the first, the kind of like biggest trick that I tend to end up using for this is I just use the fact that the simplest reflection that we can build is the poly Z operation. Poly Z, it will map 0 to 0 and 1 to -1. And so, you know, if we look at this diagrammatically, right, if we had a state like this, psi, the poly Z operation just ends up flipping the 1 component of my state vector to the minus value. So Z is a reflection. So the general strategy that we end up doing is in order to be able to carry out some arbitrary reflection, what we'll do is we'll usually do some circuit that ends up looking like a unitary transform to transform the basis that we're in into the computational basis. Then what we'll do is we'll do like a bunch of different controls on the qubits of this and apply a Z gate and then do U dagger. Okay, just because just as an ordinary Z is a reflection, a multiply controlled Z gate is also a reflection. So that's why typically if we want to be able to actually implement one of these reflections, what we'll do is we'll break it up the reflection in question into a sequence of these types of unitaries. And we'll get to that a little bit more concretely later with Grover's search. But for the moment, we can see that reflections are unitary, and we can convert any reflection we want into a sequence of controlled Z operations and use those. So let's just leave it at that then for the moment. With these two things, we've got enough in order to really be able to define amplitude amplification, or amp. And amplitude amplification, just as a little bit of history, unfortunately, that ended up coming out the year that Nielsen and Chuang was published. And so even though this is a foundational technique for quantum algorithms, it unfortunately doesn't show up in the book. It can be kind of reasoned out by looking at their discussion for Grover's search, but one of the things that I would recommend taking a look at if you want to see more details is there's a paper by Broussard, Hoyer, Tapp, and Mosca from that year, called, I think, Amplitude Amplification and Estimation. This paper is a beautiful paper that you can read that will go through many of the details that I go through. But in any case, the whole key idea of amplitude amplification is that what we would like to do is we would like to boost probability by doing a bunch of reflections. And the intuition basically is that it turns out with any two reflections, you can actually perform a rotation inside a two-dimensional space. And we're going to do this in order to generate a rotation in a two-dimensional space spanned by the states that fail to contain cake in the case of the Grover search problem, and the marked state, the good state that we want to deal with. But in order for us to really be able to talk more concretely without having to, boil down to the Grover search problem, let's define two subspaces. So I'm going to define space 1, which is the good space. Okay, these contain all the states we want to find. So for the simple case of Grover's search, which is the problem of searching for a cake, the good space would only contain this value, this vector m over here that we're trying to search for. Everything else, unsurprisingly, exists in the bad space. And these are the things that we just do not want to find. So in order for us to be able to carry this out, I'm going to end up defining two distinct projections. So I'm going to first define a projection onto the good space, PG, such that for all psi in the good space, PG acting on psi equals psi. And for all psi in bad, PG acting on psi is equal to 0. Okay. And similarly, we can end up defining a bad space projector out of this, PB, which is just equal to identity minus P good over here. And this is equivalent to, kind of us saying, let's split our space into two groups, two halves. One is the good space, the other is the bad space. And together, everything is either good or bad, which is why the identity is equal to the projector onto good plus the projector onto bad. And we can think about the identity as a projector as well. And this is just the projector onto everything. Okay, so these are the two objects that we want. And so these two objects, from them, we're going to derive, or a pair of reflection operations. And the first reflection operation we're going to define is RG, which is identity minus twice the projection, the projection onto the good space. Okay. And the second one we're going to define is RC, psi, which is identity minus twice psi. So this is the reflection about psi. Well, technically, actually, I mean a reflection about negative psi. So we'll fix this by defining a operator that I'll call W, which is equal to negative R psi RG. Okay, so before we start dealing with any of the algebraic minutiae of this particular algorithm, let me give you some intuition about how this is exactly working. So the way that this works is, imagine what we've got is we've got our state psi over here. Okay, and we want to get a good state over here. So I'm going to define a state psi g up here, which is just going to be equal to pg psi divided by the length of pg psi. Okay. And similarly, this is going to be the not so good state, which I'm going to call psi bad over here. Okay. Now, in general, psi is going to have, the probability of it being in psi g plus psi b has to add up to 1, because these two spaces will span everything. So therefore, we can always end up writing psi equals identity times psi equals the probability projector onto good times psi plus the projector onto bad times psi, which I'm going to define to be sine theta psi g plus cosine theta psi b, where in this particular case, just geometrically, this angle theta would correspond to that angle up there. And furthermore, the probability, if we just began the algorithm and tried to measure whether or not we got a success, the probability of success would just be equal to the expectation value of psi of the projector onto the good space, which is equal to, in our particular case, simply absolute value of psi given psi g squared, which is, by definition, sine squared theta. So theta here can be viewed as related to the probability of success. Theta could also be viewed as the arc sine times the square root of the initial probability of success. All right, wonderful. So this is a particular, this is how the algorithm works. Now let's just actually go through it step by step. I'm going to, for our purposes, end up writing this as R psi first, negative RG. Okay, so what I'd like to do under these circumstances is I'd like to be able to reflect about the good or negative RG, which means I'd like to take the RG component and flip it to its negative sign as the first operation. So we can understand what's going on visually just by taking a look at the diagram here. Reflecting about the orthogonal complement of G, which is what negative RG does, will map our vector psi to the exact same vector, but it will have an angle theta over here that will now be negative. In particular, this vector is going to now be RG acting on psi, or negative RG acting on psi, will be, or sorry, I don't mean a negative sign. RG acting on psi will end up giving us the negative sine theta psi g plus cosine theta psi b, which is exactly what's happened here, right? We've flipped the sign of the y component, which is the psi g component, but we haven't done anything to the x component. Now we're going to apply negative r psi, which we can view, because of the negative sign, as a reflection about the psi axis. So that is going to correspond to a reflection about here. So our angle, our state, now was an angle 2 theta below. So as I reflect it back up, now it's going to be rotated up to an angle of 2 theta here. So everything considered, these two reflections have carried out a rotation through an angle of 3 theta. So our resulting state, W acting on psi, is going to be equal to sine of 3 theta psi g plus cosine 3 theta of psi b. Okay, now in general, if we repeat this many times, what we'll end up getting is that, say, w to the p acting on psi will actually end up giving us sine of 2p plus 1 theta psi g plus cosine of 2p plus 1 theta psi b. All right. So in essence, what it does is it carries out a rotation of our initial vector in this two-dimensional plane through an angle of 2 theta. Now, let me give you an algebraic argument to justify this. You saw that what we were doing is these two reflections will keep us in this two-dimensional space spanned by RG and RB, or psi b and psi g. So we can just build this up as a two-dimensional matrix inside this space. And so the two vectors that we're going to have in it are going to be, or every vector that we have in this space will be in the span of psi g and psi b. Therefore, the action of the walk operator on psi, it can be understood as a 2D matrix in this space. Okay, so how do we end up finding this? Well, basically, because W acting on psi will always map to some linear combination of psi g and psi b, and because it's two-dimensional space, it will only take inputs in psi g and psi b. We can view this as W is equivalent only inside this two-dimensional subspace as psi GW, psi G, psi G, W, psi B, psi B, W, psi G, and psi B, W, psi B. Okay, now you might wonder, why the heck that particular form? Why the psi g's on the left? Well, if we just did matrix multiplication, let's say we had A, B, C, D on a vector E, F, well, what we end up getting is we end up getting A, E plus B, F, and then C, E plus DF. Okay, now if I break this up, I can write this in terms of the fundamental unit vectors as AE E0, or sorry, AE plus BF E0 plus CE plus DF E1. Okay, so we can end up seeing just by doing the pattern matching, right, that the first two elements in the matrix, A and B, when multiplied by E and F, will end up giving us components that are proportional to E0 in the output. And that's where the psi g's come from. So if we end up having a vector that is, these two components end up kind of grabbing the output that is in psi g, given input that's in psi g or psi b. Similarly, these two over here will correspond to outputting E1. And that's why the outputs over here are psi b, which corresponds to our E1 in this particular case. So you can see that this is the natural way of kind of writing a two-dimensional matrix in this space if we take the kind of like equivalence that psi g is equivalent to E0 and psi b is equivalent to E1. Okay, we could have flipped it and there'd be different representations for how we would do this, but fundamentally they're all exactly the same as this arbitrary choice that I ended up making. Okay, so now that we've found this expression for the action of the matrix inside this two-dimensional space, we need to do two things. One, we need to find the matrix elements. And two, we need to verify this is actually 2D. And the way we can verify that is by ensuring that the probability or the amplitudes that we end up getting for the walk operators are 1. And if they're 1, that means 100% of the probability is staying in the space spanned by G and B, which would verify that we're staying in a two-dimensional space, because 100% of the probability that starts in the two-dimensional space is mapped to the two-dimensional space and therefore remains in it. Okay, fantastic. So this is our walk operator. Now we need to go through and evaluate the matrix elements. Now, if you recall what W is defined to be negative identity minus twice the projection onto psi, and times identity minus the projection onto G. Let's go through and compute the first one. We have psi G, W, psi G. This is equal to negative psi G identity minus twice the projection onto psi. Identity, oh, there should be a 2 here, minus twice the projection onto the good stuff. Now, psi G, by definition, is in the good space. Therefore, we have that PG psi G equals psi G. And this, of course, implies that that the reflection, identity minus 2 PG psi G is equal to negative psi G, which gives us that this is equal to psi G identity minus 2 times psi G. Okay, note the negative sign here canceled this negative sign. So now we have this. However, we defined that psi G acting on psi is equal to psi G acting on sine theta psi G plus cosine theta psi B, which just gives us the cosine component. Or sorry, which just gives us the sine component here. So this result ends up giving us just 1 minus 2 sine theta squared, which is actually just equal to cosine 2 theta. Now, let's just go back for a second and see what's happening here. This cosine 2 theta from our geometric discussion entirely makes sense, right? Because when we carried out these two this reflection down and the reflection back up, we rotated an angle of 2 theta from our initial position at theta. So it's totally not surprising that 2 theta ends up coming out of this when we do our analysis this way. Okay, now let's go and do the next one. The next one that we need to compute would be psi b w, or actually, let's do the first row. Okay, now this, of course, is equal to negative psi g w. That wouldn't give us too much. This would be negative twice the projector onto psi times identity minus twice the projector onto the bad or the good space acting on the bad space. Okay, well, note that because of the fact that we're on the bad space, we have that the reflection I minus 2pg acting on psi b, that's just equal to psi b because of the fact that it is orthogonal to the axis that we're reflecting around, or because the projection onto it is 0, therefore the identity term is the only one remaining. So this is just minus psi g identity minus twice the projection onto psi, all multiplied through by psi b. And there you have it. So the next stage, we just have to figure out these inner products. Well, this inner product, well, okay, let me just expand it through. I think that'll be easiest for you to understand. Expanding this through, we end up getting from the identity term that this is the inner product of psi g and psi b plus 2 psi g psi b, okay, which of course is equal to 0 plus 2 sine theta cos theta, which of course is equal to sine 2 theta. And so there you have it. Our W matrix now, by going through this algebra, we verified that it can be written as cosine 2 theta, sine 2 theta, and then carrying out the rest of the analysis. I won't bore you with the details, but we can figure out all the rest of the matrix elements over here. We end up getting that this is sine 2 theta with a minus sign, and this is cosine 2 theta. Wonderful. And we see that this, of course, unsurprisingly, is a beautiful unitary matrix. And further, that because the all the vectors over here have norm 1, W keeps all probability in the space psi g, psi b, and it never goes outside of it. Furthermore, we can actually end up seeing that W is actually equal to, or in the space, I should say, W is the exact same matrix that we would see by Ry minus 2 theta. Okay, might be 4 theta. I hate these factors of 2 for it. But in any case, this over here is the same as Iy 2 theta. Now, the reason why, again, doing the exact same trick that we do, Taylor series expanding this guy and collecting the odd and the even terms, we end up finding that this is cosine squared 2 theta identity plus I sine, sorry, not cosine squared, sine 2 theta y. Expanding this out as a matrix gives us exactly the same thing. Gives us the cos 2 theta times identity. And using a fact that y is equal to 0, negative I 0, we end up seeing that this gives us sine theta minus sine theta. Therefore, we see that W is equivalent to Ry of 2 theta. And now using the handy dandy identity that that I asked you guys to prove on the midterm, we have that Ry of 4 theta to the P is equal to Ry of 4P theta. Now, applying this, this matrix that we end up getting from this, which is just now going to be cosine 2p theta sine 2p theta negative sine 2p theta cosine 2p theta on our initial state, which in this basis is described as sine theta cosine theta. With just a little bit of algebra and trig, we can see that this is just equal to sine 2p plus 1 theta cosine 2p plus 1 theta. Alternatively, another way that you can end up seeing this is that we have that psi is equal to psi g, or sorry, sine theta psi g plus cosine theta psi b, which is equivalent to e to the I y theta, where this is, again, I mean the y operator inside the subspace. Don't take it literally to be poly y. It's a much weirder, higher dimensional object, but the matrix that looks like poly y in this subspace acting on 0 will end up giving us psi. And so we can end up seeing that e to the I to p theta y acting on e to the y theta 0 is the same thing as e to the 2p plus 1 theta y acting on 0, which is just the result, the same result I claimed over here. So there's a couple of ways that you could see this. But whichever way you like, the key point is that applying this p times ends up changing the probability in that particular way. So the final bit that I wanted to discuss is going back to Grover's problem. How could we use this in order to solve that particular problem? Well, we have that our probability to begin with is 1 over 2 to the m. And we'd like to be able to boost this to something that's on the order of 1. So the easiest way for us to do this is, well, we're just going to apply Grover's or amplitude amplification p times to it. So we'll take our initial state psi for this problem to be Hadamard tensor n acting on 0, which of course is 1 over root 2 to the n, sum over j, using the handy-dandy identity that Hadamard tensor n acting on x is equal to 1 over root 2 to the n, sum over j, negative 1 to the x dot j, which we used extensively for the last lecture on the Bernstein-Vazirani algorithm. We end up getting now that our probability, okay, so this is our state psi. And so our reflection about psi is just, of course, going to be I minus 2 psi. And the and this reflection in particular, if you're curious, we can actually solve by using this same, or compile into a quantum circuit by using the same strategy that I discussed earlier over here. The way that we can do this is that we know that the all zero, that the state psi is Hadamard acting on all zero. So we can walk backwards. We can end up saying, okay, well, Hadamard tensor n acting on psi is equal to 0. Okay, and we want to reflect about psi, so we want to give a minus sign if the state is psi. So we want to build a quantum circuit. Then after applying Hadamard transforms, we'll map 0 to minus 0 and all other states to themselves. Well, easy way to do this is to just say that, to use the following construction. We apply Hadamards to everything. Then we apply the NOT gate to everything. And now this is mapped psi to 0 tensor n. And we've negated that. We've mapped this to 1 tensor n. So now we want to map negative 1. We want to map the all 1 state to minus itself. And that can be done by using a maximally controlled Z operation. Now we undo the basis transformations that we've done. And this circuit will carry out the exact same transformation as the required R psi. Okay. And a single query to an oracle that ends up marking the state. So let's call OF bar. All right, no, I don't mean the bit one. I just mean the OF, such that when it acts on the mark state, we get minus the mark state, means that the entire circuit for W, we can end up just writing as the following. We apply OF, and then we apply this circuit. So every action of W is a single query to our oracle. Okay, cool. So if we have this, then what does our success probability look like? Well, we start off with a state psi, which is equal to sine theta psi g plus cosine theta psi b, and WP maps this to sine of 2p plus 1 theta psi g plus cosine 2p plus 1 theta psi b. All right, so now that we have this, what's the probability of success? Well, the probability of success, if we were to just measure, this is just going to be equal to, well, the expectation value of the projector onto the states that we want of the evolved state, W psi, which when we apply the projector and we carry this through, this is just equal to sine squared 2p plus 1 theta. Okay. And theta over here is, of course, equal to the arc sine of square root of 2 to the negative n. So it's going to be a really tiny angle in general. And so we would like to get this probability of success ideally to 1. So let's set this to be 1 on the left-hand side. Well, if we set this to be 1, then we can square root both sides of the equation, and we end up getting that this is sine of 2p plus 1 times the arc sine of square root of 2 to the negative n. Okay, taking the arc sines of both sides, we find that pi by 2 is equal to 2p plus 1 arc sine of square root 2 to the negative n. Okay, which is equivalent to saying that 2p plus 1 is equal to pi over 2 arc sine of square root 2 to the negative n, which implies that p is equal to 1/2, is equal to pi over 4 arc sine of square root 2 to the negative n minus 1/2. Okay, now going through this, assuming that that this is absolutely tiny, we end up getting that this is equal to pi over 4 to the n over 2 minus 1/2 plus small correction terms of the order of 1. So this is the asymptotic scaling that we end up getting for the number of p's that we would need to boost the success probability up to 100%. Of course, the downside is, or one of the challenges is that this may not be necessarily an integer. So this is real, but not integer. So in practice, what this ends up meaning is that unless we've got a very special angle, we'll begin with some angle theta, or that's a horrible drawing, over here. And this vector is going to get rotated up as we end up applying this. Okay, and the probability will continue to increase. However, unless this number p happens to be exactly an integer here, we're going to always run into this situation where we have to deal with either under rotating or over rotating, because the exact number of rotations might not be an integer. It might be like 20 minus 1/2. And so this actually prevents us from getting 100% success probability. However, the key thing that is important for this is this scaling over here. This ends up saying that the number of times, or the number of queries that we need, goes like square root of 2 to the n, not the classical 2 to the n. And in general, for amplitude amplification, this whole exact same argument ends up applying exactly the same way. Classically, if we classically, we need order 1 over the probability of success queries in order to be able to succeed in finding or getting a vector inside the good subspace that we want. Quantumly, from the exact same argument, we need order 1 over the square root of the probability of success. Now here, the reason why it's square root, this comes about entirely because of the fact that probability is equal to psi squared in quantum. And it's this square that versus probability equals psi, classically, that leads to the quadratic difference between the performance of both of these algorithms. If quantum mechanics were different, let's say it was the fourth power over here, it's actually pretty straightforward to go through the exact same analysis and see that we would get 1/4 power instead of that. The most extreme case we could end up getting, if quantum mechanics was infinity normalized, then we would basically end up finding that quantumly, this whole process could be done in constant time. So unfortunately, quantum doesn't give us that kind of power, but it does give us the ability to be able to do it in the square root of the probability of success time. In fact, actually, we'll end up seeing later, using a technique known as the polynomial method, that actually the square root speedup is optimal. And it's impossible to, within the confines of quantum mechanics, to actually be able to do better than a square root speedup. And this is a result that's not just important for computer science, but actually for physics, because of the fact that it poses a new set of limitations on what quantum mechanics is allowed to do and not allowed to do from the perspective of information processing. So this is a really important technique that ends up getting used over and over and over again. And I should also mention, because of the fact that the only thing that we needed to assume is that we have some subroutine that allows us to check whether a solution is a good one or a less good one coming in, that this exact same formalism will end up allowing us to get a quadratic speedup for any problem that's contained in NP. So which of course is a host of hugely important problems, but it doesn't give us an exponential improvement. And in fact, people are widely believe that quantum is incapable of giving an exponential improvement for the hard instances in NP. Well, thank you very much. And so next time we're going to be covering a little bit more details surrounding the amplitude amplification before we take a break and start taking a look at its applications. Thanks a lot. See you later.